The problems that he and Hong Wang have, on which they have made a major breakthrough, those problems go back a century. A who's who of distinguished mathematicians over that century have contributed to the problem. Small improvements have been obtained by very smart people with tremendous effort. And today over the next few lectures, you'll be hearing about a major breakthrough. Cases that seemed out of reach are solved. And so prepare to be amazed. And Josh.
Thank you, Charlie. Thank you. There's a long list of people to thank. So Charlie, June, and Peter for the invitation to speak here. So I'm going to talk today and on Friday, and then Hong will talk next week about the Kakeya set conjecture that she and I have made some progress on and resolved in 3 dimensions. And the plan is that I'm not going to get into technical details today. I'm going to instead try to explain what this conjecture says and why one might care about it, although the audience in this room is, many of you are already Kakeya experts, so I apologize if today's talk is boring. Next talk on Friday, I'm going to discuss a special case of the Kakeya set conjecture that Hong and I proved a few years ago, called the sticky Kakeya conjecture. And this follows previous ideas by others, in particular Isabella Waba, Nets Katz, and Terry Tao did important work laying the path for that. And then more recently, Hong Wang and I used that special case to prove the general case of the Kakeya set conjecture in R3. And Hong is going to talk about that on Monday. And then on Wednesday, Hong is going to talk about where we go from here. Again, circling a bit on why this conjecture is important, not just historically, but for future directions. So that's the plan. And a lot of what I'm going to talk about today really centers around Princeton University and IAS. The progress on the Kakeya, almost every path of the Kakeya conjecture travels through Princeton. And okay, maybe that's true of all of math, but it's particularly true of this problem. And so let's get started. So it begins, the basic object which the Kakeya conjecture concerns is something called the Besicovitch set, sometimes called the Kakeya set. The two are interchangeable, they might slip between them. And this is defined as follows. So the Besicovitch set is a compact subset of Rn. Problem, let's make it compact. That contains a unit line segment pointing in every direction. So these objects don't have to be mysterious. The closed disk of radius 1/2 or anything larger is an example of a Besicovitch set, as are many other sets in space. But what was rather surprising was a construction due to Besicovitch in 1919 that there exist Besicovitch sets that have Lebesgue measure 0. All the Besicovitch sets. So he constructed an example in the plane. Once you can do it in the plane, might issue a phone. Oh. Wonderful. Okay, well, hopefully you could hear everything I just said. Once you can do this in the plane, you can do it in higher dimensions. You just take a Cartesian product with an interval, for example. Okay. Besicovitch's original motivation for doing this isn't so interesting to us today, but a consequence of this is if I take the delta neighborhood, which I'm going to write as k sub delta, of my measure 0 Besicovitch set, which is compact, right? The measure of this set goes to 0.
as delta goes to 0, and as we're going to see later, we're going to be very interested in quantitative estimates of this rate of decay. But I'll get to that in a few minutes. An immediate consequence of this is that for every positive eta, there exists some delta and a set of what I'm going to call 1 by delta rectangles. So rectangles of length 1 and thickness delta. I'm going to use blackboard bold T to denote this, because in higher dimensions, the analog is the delta neighborhood of a line segment, which is a tube. And a set of 1 by delta rectangles T, pointing in delta separated directions, the sum of whose areas is roughly 1. I'll say bounded below by 1, but in practice it's roughly 1. But the volume of whose union is very small. Right, so let's make sure the order of quantifiers makes sense. For every eta, I can find some very small delta, and we're going to care about the quantitative dependence between these, but I won't discuss that just yet. I can find a set of 1 by delta rectangles pointing in delta separated directions, the sum of whose area is at least 1, maybe roughly 1, and the volume of the union is fairly small. And how do I do that? Well, if I have a measure 0 Besicovitch set, I just take its delta neighborhood, and now I have the delta neighborhood of a line segment in every direction, and from this I extract a set of roughly 1 over delta lines pointing in delta separated directions, take the corresponding 1 by delta rectangles, and that's what I do here. And this construction of Besicovitch is fairly quantitative. I'm going to draw some pictures later of a slightly later construction due to Perron, but there's nothing, well, it's quite explicit and constructive. So I'm going to call this, not my name, but let's call this the Besicovitch compression phenomena. And the Kakeya set conjecture, which I'll talk about in a few minutes, attempts to understand this Besicovitch compression phenomenon a little bit better. Now, it's reasonable to ask, if you haven't seen this before, why should we care about this oddity about rectangles in Euclidean space? And one answer to that is this Besicovitch compression phenomena leads to unexpected, at least at the time, unexpected behavior for linear operators related to the Fourier transform. And to the best of my knowledge, this connection was first discovered by Charles Pfefferman in a very important result from 1971, in which this Besicovitch compression phenomena was used to come up with a negative answer to a question in Fourier summation, or in Fourier analysis. And I want to talk about that next. So this concerns the behavior of operators related to the Fourier transform. And so just to make sure we're all on the same page, if I have a function from Rn to C, I'm going to define its Fourier transform f hat of xi to be the integral e to the negative 2 pi I n x dot c f of x dx. And similarly, if I have a function g from Rn to C, I'm going to define the inverse Fourier transform and at least formally, if you take a function f and you take its Fourier transform and then you apply the inverse Fourier transform, you get back the function you started with. And now we can ask ourselves, how do we make sense of that formal expression in a more rigorous way? So we can say, maybe when or in what sense is it true that you have a function, you take its Fourier transform, you undo it, you get back what you started. So if your original function is Schwartz, then the Fourier transform is Schwartz, and there's no question about convergence of any of these integrals, and this is true in a literal and pointwise sense. Have an L2 function, then there's not too much trouble either. We understand what this means. But if you have an LP function when p is not equal to 2, then the situation's a little bit more subtle. And if your function's an LP for p bigger than 2, then already the convergence of this integral is a little bit, or the definition of the Fourier transform's a bit questionable. But let's take an LP function for p between 1 and 2, let's say less than 2, you take its Fourier transform. Now we have an LP function for p bigger than 2, taking the inverse Fourier transform again. This is a bit fraught. Now you might say, why do we care about doing this? It seems like an exercise in pointlessness to have a Fourier transform, undo it, get back to where you started. But there's many linear operators which are of the form, start with the function, take its Fourier transform, do something, undo the Fourier transform. That's a rich class of linear operators. We'd like to understand them. And perhaps the most basic question is, have a function take its Fourier transform, do nothing, and then undo the Fourier transform. We'd better have a very good understanding of all of the subtle questions related to that before we can go onwards to understand other types of linear operators related to the Fourier transform. So we have some answer to this question, and there's various directions we can go. In one dimension, over R, we could define, you can call this a Fourier summation method if you want. So T sub R of f. What I'm going to do is I'm going to take my function f, I'm going to take its Fourier transform, and I'm going to partially undo the Fourier transform. But I'm just going to integrate from negative r to r, f hat of c, e to the 2 pi I, x doc c d c. And a question I can ask is it true that as r goes to infinity, T sub r of f converges to f? And if that is true, in what sense? And certainly if f is an LP function for p between 1 and infinity, then T sub r of f converges to f in LP of r for p between 1 and infinity. And this just boils down to the boundedness of the Hilbert transform in one dimension. This is more or less, you have a function, you take its Fourier transform, you chop it from positive r to infinity, you kill that to 0, you chop it from negative r to infinity, you kill that to 0, you undo the Fourier transform. You can think of this as you have f and you compose it with two modulated Hilbert transforms. Okay, so that's well understood. What about two dimensions? Well, there's a few reasonable ways you could try to generalize this to two dimensions, right? So I mean, as r goes to infinity, the interval from negative r to positive r exhausts the reals in a very reasonable way. How do you exhaust R2? Well, there's many different ways you could do that, but two of the most obvious generalizations of this is you could integrate over larger and larger squares, or you could integrate over larger and larger balls. You could ask the same question. Do the corresponding operators converge to the identity in LP? It's for all p between 1 and infinity, if not, for which values of p? Okay, so maybe I'll write S sub r of f. This is the integral over the units, the square of side length r, f hat of c e to the 2 pi I x doc c dc. And it turns out this has exactly the same properties as the one-dimensional situation, more or less because you can think of this as an iterated one-dimensional problem. And maybe the operator bounds get a little bit worse, but not in an interesting way. Another thing you could do is you could integrate over larger and larger balls. Oops, right, B there. E sub r. And it's not hard to show that if you have an L2 function, then indeed as r goes to infinity, B sub r of f converges to f in L2. The question of whether you get convergence in this way is equivalent to the following. Is B sub 1 bounded as a map from LP of R2 to LP of R2? And when P is 2, the answer is somewhat clearly yes, because you start with an L2 function, you take its Fourier transform, you have a new L2 function, the L2 norm hasn't changed. What is this doing? If R is 1, for example, you're multiplying by the characteristic function of the ball, so you're killing it everywhere else. That can only decrease the L2 norm, and then you're undoing the Fourier transform. So this, when P is 2, this can only decrease the L2 norm, and indeed the operator norm is 1. So this is why this is called the ball multiplier. You have a function, you take its Fourier transform, multiply it by the characteristic function of a ball, undo the Fourier transform. Right? This is an example of a Fourier multiplier. We want to understand the LP boundedness of, amongst other things, Fourier multipliers. This is a rich class of linear operators. And what Pfefferman proved in 1971, which I think was rather unexpected, to put it mildly at the time, is that p equals 2 is the only value of p for which this operator is bounded. So maybe I'll write it like this. I'm going to use capital B for B sub 1. So this is the operator, the Fourier multiplier associated to the unit ball. So B is a map from LP of R2 to LP of R2 is infinite. The operator is unbounded as a map from LP to LP for P not equal to 2. Okay, so I won't give you his full proof, but I want to give a sense of what this proof does, and in particular, why the Besicovitch compression phenomena plays a role in this proof. So here's a proof idea, right? So what does it mean for this operator norm to be infinity? It means for every large number c, I can find a function f so that when you apply b to f, it increases the LP norm by at least c. So you can do this for every c, you're golden. So here is an idea of the proof. So it's a proof by contradiction. If this guy had operator norm less than c, or say less than or equal to c, then that would also imply the operator norm boundedness of a vector valued operator, which I'm going to tell you what it is. So if this was true, then if you take n unit vectors, what I'm going to say is uniform in n. So if I take v1 through vn, these are unit vectors in the plane. And functions f1 through fn in LP of R2. Then I'm going to have the boundedness by a most constant c of the following expression. And so in what I'm about to say, h sub I is the Hilbert transform, capital H, associated to the half plane. Maybe I'll just say the Hilbert transform in direction vi, and I'll draw a picture. So what do I mean by that? So what is a Hilbert transform in one dimension? You can think of it as a Fourier multiplier. You have a function, you take its Fourier transform, and then you multiply it by the characteristic function of, let's say, the positive real numbers. So you kill it on all of the negative numbers, and then you undo that. And there's some multiplicative factor out in front, which we don't care about, what I'm about to say. So in 2 dimensions, what I'm going to do is I'm going to take a plane with normal direction vi, and the corresponding Hilbert transform, you have a function, you take its Fourier transform, you multiply it by the characteristic function of this half space. Sorry, I said plane, I meant to say half space, and then you undo the Fourier transform. So if this operator had operator norm at most c, then the following would be true. What I'm going to do is I'm going to sum the Hilbert transform hi applied to fi squared, take a little L2 norm, and take a big LP, this is in the plane norm of this, and this would be bounded by at most c times the same expression without the h's. Okay, now, this implication requires a proof, which I'm not going to tell you, but just to give a very rough sense. So what makes the unit ball different from the unit square is that the unit ball has a lot of different normal directions. In fact, it has every possible normal direction. And so for each one of these unit vectors, v sub I can take the unit ball and shift it and rescale it, and that little piece, a little piece of the unit ball after the shifting and rescaling begins very closely to resemble this half space, at least at the scale that you're looking at. And so if this Fourier multiplier associated to the unit ball was bounded for some value of p, you get the corresponding operator norm bound for this kind of expression. And now our goal is to find a counterexample to this statement, right? So you give me your favorite c, I need to find a collection of vectors v1 through vn and corresponding functions fi to violate this inequality. And how am I going to do that? Well, I'm going to use the Besicovitch compression phenomena. And so what I'm going to do is I'm going to pick an eta, which is very small compared to capital C, and I'm going to find a collection of rectangles of length 1 and thickness delta, whose union is very small. So maybe it looks something like this. I'm drawing a little piece of the Perron tree construction of a measure 0 Besicovitch set. Okay, maybe this picture is not that convincing, but the idea is I have roughly 1 over delta rectangles of length 1 and thickness delta, and their union is very small. Their union has volume roughly eta. And I'm going to call these guys blackboard bold T, this set. And then I'm going to shift each one of them by distance roughly 1 in the direction that it points. And after you do that, they don't quite become disjoint, but they become substantially more disjoint. And for the purpose of this illustration, I'm going to pretend that they become entirely disjoint. Okay, these are all still supposed to have length 1 and thickness delta. And this new collection I'm going to call T tilde. Oops. Let's try a different color. Okay. Now what am I going to do? So each one of these is some Ti, and it points in direction V sub I. Those are all distinct from each other. And more or less what I'm going to do is I'm going to let F sub I be the characteristic function of these T sub I tildes. So what's happening? This is a function. F sub I is 1 on this shifted rectangle. And the direction of the rectangle is the vector Vi. Let's see what happens with this example. So what is this right-hand side? Well, I have this sum of characteristic functions. If these guys are all disjoint from each other, which I'm going to pretend is in fact the case, then squaring it does nothing. And what this begins to look like, and also taking a square root does nothing. So this is the LP norm of a function which has size 1 on a set of roughly size 1. The right-hand side is just 1. Okay, that's easy to understand. What about the left-hand side? So now the question becomes, what does this Hilbert transform in the direction Vi do to this function? And very roughly what it does is it blurs it out in this direction that you are pointing. And in particular, what is going to be the case is that when you apply, let's see if I can clean this up a little bit. When you apply H sub I to F sub I, this thing has size roughly 1 on this set here, which is T sub I. And so now what is going on is if I want a lower bound on this quantity, I can restrict my integral just to the union of these tubes. And what's going on now is on the union of these tubes, I have a sum of functions which are roughly 1. They begin to stack up a lot, right? Because the L1 norm of this thing is roughly 1. It's a sum of roughly 1 over delta, functions, each one of which has mass delta. But the support of all these functions has area only eta, which is much, much smaller than 1. So what this is telling me is these functions are beginning to stack up. Take a square root. If p is bigger than 2, right, integrate this thing. Sum of the HIs. The moment this exponent is bigger than 1, i.e. the moment p is bigger than 2, this guy here is blowing up, right? So hopefully what I've just said is clear. This thing is blowing up because its L1 norm is roughly 1, but its support is compressing a lot. And that causes, the moment this exponent is bigger than 1, this causes blow up. And that gives me a contradiction to this statement here. So if p is smaller than 2, strictly smaller than 2, you can do something involving duality. So this is more or less the entirety of Pfefferman's proof. And it's important to understand what's going on. So we have this operator, which involves oscillation. And in order to show that it is unbounded, we are coming up with a particular example where we have functions supported on these very eccentric convex sets, these long, thin rectangles, and we're compressing their support to cause the LP norms to blow up. Okay, so now we can talk about the Kakeya set conjecture. Maybe I will keep this, maybe I'll get rid of this. So the one way of thinking about the Kakeya set conjecture is you could ask just how bad is Charles Pfefferman's blowup, or the blowup in the ball multiplier as found by Charles Pfefferman's example. And how bad is that blowup? Well, it depends on how much Kakeya compression or Besicovitch compression you can achieve. And you can get an arbitrary amount of Besicovitch compression at the cost of making these rectangles extremely thin, and we might want to understand some quantitative dependence on that. Another way of stating it is just how extreme can this Besicovitch compression phenomena actually be? And what the Kakeya set conjecture says is Besicovitch compression exists as evidenced by this construction of Besicovitch, but only a subpolynomial amount in delta. So that is what this conjecture says. It's often stated in slightly different language, so I'm going to state several variants of this conjecture. So most of these statements are not equivalent, but there are formal dependencies and moral dependencies between them. So maybe I won't even number them, I'll just use bullet points. So the first is every Besicovitch set in Rn has Minkowski and Hausdorff dimension n. So if you have Hausdorff dimension n, that certainly implies that you have Minkowski dimension n. So there's a little bit of redundancy in this statement. On the other hand, there have been times when it's been easier to prove Minkowski dimension bounds than Hausdorff dimension bounds, so this gives some wiggle room to talk about both, and maybe hedge bets. Another, what you could call a discretized version of the statement is the following, and so this is a statement involving quantifiers, and so it can be written as follows. For every positive epsilon, there exists some number c, which is allowed to depend on epsilon and the ambient dimension n, such that the following is true. Let T be a set of delta tubes. I'll tell you what those are. I said it out loud a minute ago, but I'll draw a picture. In Rn, so what is a delta tube? It is, you can think of it as the delta neighborhood of a unit line segment, or if you want, you can think of it as the delta neighborhood of a unit of a line segment, which is then chopped to have length 1. These are more or less the same. You have this tube has a coaxial line, and that coaxial line has a direction, and that's going to be called the direction of the tube. So let blackboard bold T be a set of delta tubes in Rn pointing in delta separated directions. So this is the generalization of what I did over there in the plane. Then, the volume of the union of these tubes is almost as big as the sum of the volumes up to a sub-polynomial factor, which is precisely what the Kakeya compression phenomena, or the Besicovitch compression phenomena, shows us has to exist. So I'll write down a precise statement. So the volume of the union is bounded below, I'm going to write something here, by the sum of the volume. So if these tubes were truly disjoint, then this inequality would be true. You could maybe hope for some small constant here, but we know that no fixed constant independent of delta could possibly make this inequality true because Besicovich's construction shows that for any positive eta, I can find a sufficiently small delta so that this inequality is violated even with constant eta. But what is true, or rather what the conjecture says, in which we do not have a counterexample for, is an inequality of this form. So for every positive epsilon, there exists some c, which depends on epsilon and the ambient dimension, to make this true for every family of tubes pointing in delta-separated directions. And this precise quantified statement is used so often in this area that there's even a special notation for it. I don't know the origin of this notation. Some have attributed it to Terence Tao. So some people call this Terry-Tao notation, but I don't know if that is the true attribution. But whenever you see I wrote that rather messily, a greater than double squiggle, that is hiding a quantified statement. For all epsilon, there exists some constant c depending on epsilon and the ambient dimension, so that this quantity is bounded by this quantity, where these are implicitly functions of delta. Okay, so what is this saying? I'll just say it one more time. Besicovitch compression can exist as evidenced by Besicovitch's construction, but only a sub-polynomial amount. What would a polynomial amount be? It would be a collection of tubes where this inequality is violated for some concrete exponent here, maybe 0.01 in R4, for example. If you had such a family of tubes where this inequality was violated along a sequence of deltas going to 0, that would be a counterexample to this statement here, and presumably a counterexample to the Kakeya set conjecture, although that would depend how these tubes change along that sequence. But these two statements morally are the same. At least this one is morally the same as the Minkowski dimension version of the conjecture. And the Hausdorff dimension version of the conjecture is morally what this is saying here, except instead of having the entire tube, you could replace it with a shading on the tube, which contains a fairly large fraction. And I won't state that for you precisely, but I'll state one more version of the conjecture, sometimes called the Kakeya maximal function conjecture. That says the following. There's several equivalent formulations of it, but I'll state a version which is most closely analogous to what I've written here. Maybe I'll state two versions. So just to reiterate, the first statement I wrote is what is agreed upon as the Kakeya set conjecture. The second statement here you might call the discretized Kakeya set conjecture, if you want, or at least a discretization of that conjecture. And then this third object I'm going to write, or this third thing, is the Kakeya maximal function conjecture. And I'm going to have the same hypotheses as I had here. So let T be a set of delta tubes in Rn pointing in delta separated directions. All of that remains the case. And then for each tube in my collection, I'm going to take a subset of the tube, which we often call a shading. It's just let's say a measurable subset. And I'm going to call that y of t. And how much of the tube is present? Well, at least a lambda fraction, so lambda is a parameter. So then I want a lower bound, not just on the union of these tubes, but on the union of the chosen subsets. So I'm going to use the same notation, suppressing that quantified statement. And what is the appropriate power of lambda? Well, it's not hard to convince yourself that if this is true for, well, anyways, this is the best exponent you could hope for. So maybe some of you have seen other formulations of the Kakeya maximal function conjecture. This is one that in practice is sort of easy to get your hands on. Another way you could state it is if you have a collection of tubes pointing in delta separated directions, you could consider the sum of the characteristic functions of those tubes. And we could consider various LP norms of that sum of characteristic functions. And intuitively, if these tubes are disjoint from each other, then larger LP norms should still be not particularly large, right? The L infinity norm could be as big as the number of tubes. The L1 norm is just the sum of the volumes of these tubes, which is bounded by 1 if they point in delta separated directions, or at least an absolute constant, depending only on the dimension. And what the Kakeya maximal function conjecture says is that the critical exponent is n over n minus 1. And this is controlled, let's raise this to the power of n over n minus 1 to make this a bit cleaner. This is controlled by the sum of the volumes of the tubes. So these tubes are disjoint not only in a volume sense, but also in an LP sense up to some critical exponent here. Okay, so these are various not quite equivalent conjectures, but this conjecture here implies, the discretized conjecture implies the original conjecture. Maybe I'll pause for one moment. Are there any questions about what I've said so far? Okay, there'll be time for questions at the end as well. So I'm going to talk briefly about what has been done for this conjecture. So in 2 dimensions, the Kakeya set conjecture was proved by Davies. Maybe I'll here, that's fine, by Roy Davies in 1971. And the maximal function conjecture was proved by Cordoba in 1977. With the benefit of hindsight and all of our sort of modern tools, one could, well, let's just say earlier work by Pfefferman on the restriction conjecture also implies the Kakeya maximal function conjecture, but we certainly didn't know that at the time. But this certainly, Cordoba proved it in more or less the formulation we've been stated here in 1977. And in 3 dimensions, less is known. But the reason that I'm talking to you today and that Hong will talk to you next week is that the Kakeya set conjecture Hong and I proved this year. So I'll say Kakeya set conjecture. So this is Wang and Zahl. 2025 plus. The maximal function conjecture we did not prove. That looks potentially rather hard. And in higher dimensions, the question is still open. There's been partial progress. Partial progress can mean different things. It can mean, in some cases, proving very special cases of the conjecture, or more typically for what's been done, it can mean we can show that every Besicovitch set in R4 has Hausdorff dimension at least something where something falls short of 4 that gets you partway there. And similarly in higher dimensions. So I won't talk very much about what's been done in higher dimensions. I want to talk a little bit about this recent result in 3 dimensions, and I want to write down a concrete theorem. So one concrete theorem is every Besicovitch set in R3 has Minkowski and Hausdorff dimension 3. That is a true statement. What is also true is a discretized statement of this form, but part of what allowed Hong and I to prove our result was the realization that actually this is perhaps not the right question to be asking. There's a slight generalization of this condition, which is easier to work with. And the property of pointing in delta-separated directions is arguably a bit of a red herring. That's a debatable statement, but that is a viewpoint that was helpful for us, I can say. So I'm going to state concretely what Hong and I proved. And quick question, how long should I talk for? Should I end at the 20 or the 30 minutes off the hour? 25, okay, split the difference. Wonderful, okay. Thanks very much. So here's a theorem due to Hong and myself. And so again, there's a quantified statement for all epsilon there exists a C, but I'm going to suppress that in that double squiggle. So it's the following. Everything's in R3. If I forget to say R3, that's true for everything I say for the remainder of today. So let T be a set of delta tubes, okay, in R3. And if I was just repeating what I said here, then I would say pointing in delta-separated directions, but I'm going to say something new. I'm going to say that satisfy the Katz-Tau convex Wolf axioms. And I'll tell you what that means in just a minute. I'm going to come back to this, of course, otherwise the statement is meaningless without defining this. So then you get the result you want. No, that's not what we want. Okay, so that is the correct conclusion. Somewhere, here we are. And in fact, we prove a slightly stronger thing. So this in particular implies that, well, modulo not knowing what this means, this implies that every Besicovitch set in R3 has Minkowski dimension 3. In fact, we proved something a bit stronger. We proved that every Besicovitch set in R3 has Hausdorff dimension 3, and we proved something that looks a little bit like a very weak form of a maximal function estimate, which nonetheless is sufficient to imply all the other statements. And so there's a few ways of stating the maximal function result, but maybe the cleanest is, so I can say for all epsilon, there exists some p which is strictly bigger than 1 and some large constant c, so that, again, under these same hypotheses, the sum of the characteristic functions of the tubes, the LP norm to the p, is controlled by the volume of the tubes. So if p equals 1, I mean, there's nothing to do here. And the moment you can prove an inequality like this a little bit past 1, this is telling you that the tubes are not concentrating into a region whose size is delta to any fixed power, right? So the support in some fairly strong LP sense has size which goes to 0 in a subpolynomial fashion. Okay. Our p depends on epsilon. The Kakeya maximal function conjecture says that this should always be true for p equals, in R3, 3/2, regardless of epsilon. So that's what we prove is far short of the maximal function estimate. But nonetheless, it tells us something interesting about the geometry of tubes in R3 and more generally convex sets in R3. But I haven't told you what this means. So Tom Wolfe played a very important role in the study of the Kakeya set conjecture. And in 1995, he wrote an influential paper in which he proved that every Besicovitch set in R3 has dimension at least 5/2, and he proved various stronger statements of that flavor. And he proved it for a more general class of objects than just Besicovitch sets. In the discretized setting, he proved it for more general families than just tubes pointing in delta-separated directions. He realized that the real enemy to the Kakeya set conjecture is if tubes cluster into planes. And that's not surprising, because a plane in R3 is the only infinitely ruled surface. And so somehow the infinite ruling by lines, if you thicken this, this gives you a way for a lot of tubes to cluster into a small region in space. And this is the only enemy, is one of the consequences of our theorem, but I think Tom Wolfe already realized that this was probably the case. And so a family of tubes satisfies the Wolfe axioms if not too many tubes are allowed to concentrate into the thin neighborhood of a plane, or more generally, into a convex set, which is, for us in R3, just the thin neighborhood of a plane intersected with a thickened tube. Those are the only relevant convex sets. And exactly how many tubes are allowed to concentrate into such a region? Well, we want an inequality which has to do with the volume of that region. And this looks a little bit like something called a Katz's tau set from discretized incidence geometry or geometric measure theory, where they were interested in some discretized analogs of questions in geometric measure theory. They wrote down a non-concentration condition, which is a little bit like Frossman's condition for a Frossman measure. And that's where this Katz's tau business comes from. This is describing the kind of non-concentration we need. Hong might talk a bit later about a different non-concentration condition called a Frossman non-concentration condition. That just gives you a sense of this terminology. But let me define what this is. So here's a definition. So we say T satisfies the Katz's tau convex Wolfe axioms if for every convex set we're in R3. Well, this is true in Rn, but I only care about R3 for now. For all convex, let's call it W, at most, the volume of W divided by, I'm going to write this as, so it's the volume of W divided by delta squared, but I'm going to write delta squared as the volume of a tube. All these tubes have the same volume. Tubes from Blackboard Bowl T can be contained in W. I can phrase that a bit differently. I'm going to say the same thing a second time. Occasionally that's helpful. So equivalently, if you sum the volumes of all the tubes contained in W, this is at most the volume of W. And so if this failed, this would fail very dramatically, for example, if you have delta to the minus 2 tubes in R3, that's the correct number, as if they were pointing in delta-separated directions, but maybe instead they're all contained in the delta neighborhood of a plane, all inside the unit ball, let's say. That would be a dramatic failure of the conclusion of the Kakeya set conjecture. And how does this fail? It's because they're all packed very tightly into a plane. That's not allowed if the tubes point to delta-separated directions. More generally, it's not allowed if the tubes satisfy the Wolf axioms. So what this is saying, this theorem, is if you have a collection of tubes, or more generally of convex sets in R3, everything's inside some compact region, what are the enemies to these tubes being almost disjoint from each other? Well, the Besicovitch compression phenomena, as discovered by Besicovitch, says you can have a subpolynomial amount of compression. That's just a feature of Euclidean space we have to deal with. And the corresponding unboundedness of certain linear operators, well, that's simply the world we live in. But beyond a subpolynomial amount of compression, the only way that can happen is if your tubes are concentrating inside of the thickened neighborhood of a plane, or more generally, inside of a convex set. So that's what this tells you here. In higher dimensions, the statement makes sense, but it is false as written, because in R3, the only surface that contains a lot of lines, and the only surface that's infinitely ruled by lines is a plane, and then the only enemy is a thickened plane. But the moment you're in R4, there's other infinitely ruled surfaces. There's degree 2 quadric hypersurfaces that are infinitely ruled by lines, and those create new obstructions. So there's reasonable conjectures you can make in higher dimensions, but you have to broaden the class of obstructions to the Kakeya set conjecture. Okay, hopefully the statement makes sense. I have about 10 minutes left, so I want to spend the last 10 minutes talking about why we still care about the Kakeya set conjecture. I mean, Pfefferman's example was certainly one reason we were interested in it, but that didn't entirely close the book on that question. It, in fact, posed future questions, but from what I've said so far, it's maybe not clear what those future questions are. And I want to talk about Eli Stein's Fourier restriction, Fourier extension conjecture. So for those of you that are familiar with this conjecture, I apologize. I'm not going to say much that's new, but for those that aren't, I think this is a rather unexpected, again, connection between the LP mapping properties of linear operators associated with the Fourier transform, and as we're going to see, also some local smoothing type questions about the behavior of solutions to the free Schrodinger equation, and this Kakeya compression phenomena. And to the best of my knowledge, this connection was discovered, at least in the way I'm going to talk about it, by Jean Bourgain in the early 90s. It might have predated him, but certainly in writing what I've seen is due to him. So another lion of the Princeton and IAS world. So let me define Stein's Fourier restriction and extension conjecture. So the two are, often it's called the Fourier restriction conjecture, but what I'm going to tell you is technically the Fourier extension conjecture. The two are duals or adjoints of each other. So the Fourier restriction conjecture concerns the restriction operator. I'm going to tell you the extension operator, but same question. So if I have a function, well, first of all, I'm going to work in R3 for everything I say. And I'm going to be interested in the paraboloid, which is going to be given by x3 equals x1 squared plus x2 squared, easy to understand. And sometimes I'm going to restrict myself to a compact region in space, and so I might intersect with, let's say, the unit ball or the ball of radius 2, and I'm going to be a little fast and loose about when I'm dealing with the entire paraboloid versus this restricted region, at least for the time I have left. And if I could have a function, f, which is supported on this paraboloid, takes values in C, and I'm going to define the extension operator associated to f to be f d sigma inverse Fourier transform, where what is d sigma? D sigma is going to be the lift of, it's going to be a measure supported on this paraboloid, and what is this measure, just take Lebesgue measure on the plane and lift it to this paraboloid in the obvious way. Okay, so this is now a function supported in R3, or at least a distribution supported in R3, and we can ask for which p, or maybe I'll just say here's a conjecture. So this is an LP function in R3. Conjecture says is bounded by the LP norm of f on the paraboloid for p bigger than 3. So 3 is the critical exponent. Okay, so not entirely clear why this is an interesting. There's various reasons why one might study this object. Some of them come from restriction theory. So you have a LP function, you take its Fourier transform. In what sense can we meaningfully restrict it to a hypersurface, or a surface in this case? And it turns out the answer will depend on the curvature of that surface. I don't want to talk about that right now. Instead, I want to talk about the free Schrodinger equation. So let's say I have a function, let's say the free Schrodinger equation in 2 space and 1 time dimensions. I have a function u of xt, and it satisfies, so apologies to the math physicists, there's some pi's here because of how I defined the Fourier transform earlier. Negative 2 pi I, the time derivative of u, plus the spatial Laplacian of u is 0, and some initial condition u of x 0 is u naught of x. And okay, so maybe one doesn't require too much justification to say this is an object we would like to understand. What does it mean to satisfy this PDE? Well, if I take a Fourier transform, and let's say I associate x with c and t with tau, then this becomes, after pulling out some 2 pi I squareds, tau minus magnitude of xc squared times mu hat of xc tau equals 0. Right? One of the critical things about the Fourier transform is that it intertwines differentiation and multiplication. What is this telling us? Well, if this thing is 0, either the left-hand side or the right-hand side has to be 0, or both. And so what this means is that the support of u hat is contained in the paraboloid. So that's kind of interesting. Functions which satisfy the free Schrodinger equation on the Fourier side, they have support on the paraboloid. And there's similar situations for other surfaces. Functions which satisfy the wave equation have Fourier support on the cone. Functions which satisfy the Helmholtz equation have Fourier support on the sphere. And as it turns out, understanding the LP mapping properties of the extension operator tells us something about the LP mapping properties of the linear operator, which, given initial data, solves the free Schrodinger equation for that initial data. Let me just write down what that is. So we can say, given initial data, u naught of x, let's solve the free Schrodinger equation. And what is it given by? You apply the extension operator. So u naught of x is a function of 2 variables from R2 to C. I'm going to take its Fourier transform, u hat, and then I'm going to lift that to the paraboloid in the obvious way, where for each point on the paraboloid, I define my value to be the lift of u hat to that paraboloid, and I'm going to call that f. Where what is f? So I said it out loud, but I'm just going to say it one more time. You give me some initial data u naught for the free Schrodinger equation. I take its Fourier transform. That's a function from R2 to C. I lift that to the paraboloid in the obvious way. For each point, the value at that point is just the value of u hat downstairs. This is a function now supported on the paraboloid. I take that function d sigma, where sigma is the lift of Lebesgue measure on the paraboloid, take the inverse Fourier transform. I hope you will agree that is a function from R3 to C, and that solves the free Schrodinger equation. So this kind of question here is asking, or proposing, that this operator, which describes solving the free Schrodinger equation given initial data, is bounded from LP to LP when P is bigger than 3. And this is telling you something about the free Schrodinger equation being a dispersive PDE. Energy disperses over time. How can you capture that idea? Well, certain LP norms for P bigger than 1 remain integrable across across all of time. That is a quantitative version of dispersion. Okay, maybe I'll borrow 2 more minutes to say how the Kakeya set conjecture is related to this question here, because that doesn't appear entirely obvious. And I'll have to be a little bit fast and loose. But one observation is to prove an inequality of this form, you don't actually have to integrate over all of R3. You can instead integrate over some large ball of radius r. You can weaken this inequality slightly and lose a subpolynomial factor in r. If you can prove an inequality of this form for every ball of radius r, and the constant here only depends on epsilon for every epsilon, then through a technique called the epsilon removal lemma, you can recover the original Fourier restriction conjecture. And if you're integrating only over a ball of radius r, then the function whose Fourier transform is supported on the paraboloid, you can blur that out at scale 1 over r, and you really can't see the distinction anymore. So instead of having a function supported on the paraboloid, you might as well have a function supported on the 1 over r neighborhood of that paraboloid. And something which turns out to be a good idea, to the best of my knowledge, discovered or at least talked about first by Jean Bourgain, is you can decompose this paraboloid, or the 1 over r neighborhood of this paraboloid, into a bunch of little regions. I might call these coins. So what is a coin? A coin is fairly small, but it's much thinner than its diameter. What is the dimensions of these coins? These have width r to the minus 1/2 and thickness r. Thickness 1 over r. Those are the natural dimensions of the largest convex set that you can put inside the 1 over r neighborhood of the paraboloid. And I cover my paraboloid by all of these pieces. And if I have a function whose, well, in this case, my function f is supported on the paraboloid, and thus its 1 over r thickening is supported on this 1 over r thickening of the paraboloid, it decomposes into a sum of pieces, each of which have disjoint supports. And my linear operator EF becomes the sum of E of Fi as I is summed across all these pieces. So I get this F1, F2, F3, so on and so forth. Maybe I'll use one more color. And the point is, what happens when you take the inverse Fourier transform of a function supported on a little convex set like this? Well, the Fourier transform of a function supported on a little convex set like this is roughly constant on the dual of that convex set. And what is the dual of this convex set? It is a tube. It's somewhat long, but much, much thinner than it is long. I'll draw a picture. It is a tube in space. And the direction this tube is pointing is exactly the normal direction of the paraboloid at that point. And similarly for what's going on here. So what you can do is you can take your function which is supported on this thickened neighborhood of the paraboloid, you decompose it into these little caps, you apply the extension operator, which is just an inverse Fourier transform, to each one of those pieces, and now you have functions that are at least well understood. Their absolute value is roughly constant on these tubes. Now there could be multiple parallel tubes, but one of the most interesting situations is where each one of these pieces, the inverse Fourier transform, is really only supported on a single tube. That's one special case that we care about. And this starts to look a lot like the situation of the Kakeya set conjecture in R3. You have a bunch of functions whose support is on these tubes pointing in delta separated, or I guess in this case delta is 1 over root r, separated directions. And how can the LP norm be large? Well, one way it can be large is if this support compresses a lot. If that happens, then that forces the LP norm to be large. And that would be a counterexample to the restriction conjecture. Another way it can be large is perhaps the support doesn't compress all that often, or these tubes don't intersect all that often, but where they do, you get a lot of constructive interference. And so morally speaking, what this Fourier restriction conjecture says is after you apply this, what's called a wave packet decomposition, you get these functions supported on tubes pointing in different directions. And they don't intersect all that much. The volume of their union is at most what is given to you by the Kakeya set conjecture. And where they do intersect, you have complex phases, but they constructively and destructively interfere with roughly square root cancellation. And that second part we don't know how to do. But the first part of understanding the support of these functions, well, we've made a lot more progress on that, at least in 3 dimensions. Okay, I'll finish there, so thank you.